Black holes. You may find it very weird, right? I mean, do they follow the same physics we follow? Yes, they do. While they are very confusing and we do not know too much about them, we do know that black holes follow the laws of thermodynamics. But before that, what even is thermodynamics? Thermodynamics is a branch of physics that talks about heat, work, temperature, and how they are related to energy. Actually, thermodynamics was a study that sprouted out of the need to make engines and other machines more efficient, essentially to produce the most work for the least amount of energy. Think of a car's fuel efficiency. Most buyers would buy cars that go the farthest for the least amount of fuel, as it's getting very expensive these times. Now that we know what thermodynamics is, we can talk about how black holes follow the 4 laws of thermodynamics. The zeroth law. This law states that if two objects are in the same temperature or thermal equilibrium with another object, then all of them are the same temperature or thermal equilibrium. The significance of this law is that it shows temperature is a property of matter that can be measured of all objects. While it doesn't really explain it directly, you could say that when these objects are in equilibrium, we could use a number to have a measure for the temperature. It's pretty abstract, I know, but it's the framework for all of the other laws. So in simple terms, this law just states that everything has a temperature. But how do black holes apply to this? Well, that's because they do have a temperature. See, have you ever heard of thermometer guns? The ones that detect infrared light being emitted from objects and measure the temperature? In that same way, we can detect black holes through their waves. But black holes don't put out anything, they take in everything, right? That's where Hawking radiation comes in. But before that, I just want to say that the explanations for this in this video are going to be very abstract from the actual definition. This is astrophysics that has links to quantum mechanics, so to help you and me understand, I will have to provide an explanation that is not exactly what happens. See, in space, there are always particles being created, antiparticles and particles. These spontaneously pop into existence and both cancel out each other. But when this happens right at the edge of the black hole eats one of the particles in the pair and the other escapes. But it can't just escape, it's gonna need energy. And this energy comes from the mass of the black hole. In essence, this is how a black hole evaporates. But it's these particles that get launched out that become the waves we detect to find out the temperature. These particles can be photons, which are the particles for light. Think of how a light bulb gets so hot that it produces visible light. Now, let's move on to the first law of thermodynamics. The first law of thermodynamics basically states that energy cannot be created or destroyed, only transformed. We've already seen black holes do this. They gain mass by eating gases, stars, and many other forms of matter, and they lose energy by Hawking radiation. They don't just eat energy and keep it there, they also emit it. Next, the third law of thermodynamics. But you skipped the second law. There's a reason for this. The second law is a bit more complicated and is more unrelated, so I'll be talking about it last. The third law states that it's impossible to reach absolute zero. If you didn't know absolute zero, it's the lowest temperature something can go. All the atoms stop moving at this point. There's zero heat in the system. See, black hole temperature is related to its size. The smaller the black hole, the hotter it is, and the larger it is, the colder it is. This is one of the sides of astrophysics that is hard to explain. See, in our model of black holes emitting Hawking radiation, the smaller black holes have higher frequencies and the bigger black holes have lower frequencies of wavelength. If we were to measure the temperature of this, the only conclusion we have is that bigger black holes are colder than smaller ones. Black holes still have equilibrium with their environment as per the zeroth law. It just happens when they fully evaporate. So if bigger black holes are colder and smaller black holes are hotter, then if the black hole reaches absolute zero, aka the coldest ever, then the black hole would have to be infinitely big. But that wouldn't happen because black holes are inside of the universe, meaning that they're smaller than the universe, not infinitely big, meaning that black holes can't reach absolute zero. Lastly, the second law of thermodynamics. This states that energy, instead of being consolidated into one area, spreads until it's even over time. This is called entropy. Weird to think about, right? Think about cooking something in a pan. In a perfect world, you would think only the stove would heat up the pan and the food only. But in reality, the pan, along with its handle and the surroundings, heat up. You can feel the heat in the air. That's because the heat energy doesn't just stay in the pan, it spreads everywhere, and this happens over time. See, having low entropy means energy consolidated into one place, and high entropy means energy being spread evenly around the place. So if black holes can eat up these masses and become big, wouldn't that mean that's a ton of energy in one place? But that's when Hawking radiation saves the day again. Since black holes emit radiation that comes from these particles stealing the mass of the black hole, energy is being spread again. This was actually the reason Hawking radiation came to be. Jacob Bekenstein conjured that black holes have entropy that is proportional to its surface area. To prove this right or wrong, Stephen Hawking did his research, and that's when he found out about Hawking radiation and the spreading of energy, thus proving Bekenstein right. And that's how black holes follow all the laws of thermodynamics. On a final note, these concepts are very difficult to understand. Some of them are part of quantum theory, and so much maths go into this. I have left out all these details for the sole purpose of at least giving an easier understanding of these topics. But this is the bare bones understanding you need for it to be a foundation to go deeper into these interesting topics. And that was the whole point of this 3-video project, to help people understand and equip them with the knowledge and inspiration to not give up on their research. Thank you for watching.